imaginary exponential as it, figures into the polar decomposition of a complex number last time, right? So we're still good on that. What's the modulus of e to the z? So I think the formula that you want to use here is that one. Right? And the reason you're saying that is because the modulus of the product is the product of the moduli, but the modulus of an imaginary exponential, that's a point on the unit circle. Distance is 1, length is 1, so that's 1. What's the modulus of e to the x? Well, it's a real quantity. It's just positive. So like you said a minute ago, e to the x. Yeah. So is the complex exponential ever 0? Its modulus is e to the x. Can that be 0? It cannot, right? So theorem, e to the z is not equal to 0 for all z in the complex plane. Woohoo! The complex exponential is non-zero. In fact, the range of the complex exponential is what we call c with an x on it. This is, specifically c minus the origin, the so-called punctured plane. Yes, sir.
So would you basically use the modulus of e to the z to extract components from the z? Like you could take you could try and take the conjugate of e to the z and then take the modulus of that, and you would probably get e to the y, right? So then you could just take the natural logarithm and you get y.
Well, I don't know about all that. This is the definition. It naturally rises from the power series, and yes, sir. I don't know. You'd have to ask me in office hours. I'm sorry. What?
I'm confused on how we went from the magnitude of e to the x times the magnitude of e to the iy equals e to the x.
Oh, that's because this is 1.
How do we know that that's 1?
Work it out. That's the square root of cosine squared y plus sine squared y. So, yeah. Now, the log of z is the natural log of the modulus of z plus I times arg of z. So this is the principal logarithm. We use the principal argument to write the principal logarithm. You can also talk about the multiply valued log. Little log of z is equal to the natural log of the absolute value of z plus I little arg of z. So it's a set of values, all right? And I think in my notes I also define like log sub alpha, which uses the argument based at alpha, all right? So I spent too much time writing about principal roots, so I'm not going to write that on the board at the moment, okay? Okay, so then what? Well, this is, of course, actually, you can prove that this is the inverse function to the exponential. This formula is only, what's the domain of the log? It is the punctured plane. All right? So, unless we want to make the log continuous, in which case we have to do a little bit more. We have to remove a ray, because the log is discontinuous if that's the whole domain, because there's an angle jump. So if we want to make the log continuous, we have to like throw out something in there, a ray from the origin. More on that later. Now, let's see here. What would the, you could, actually that's all I want to say about that for now. So you have some homework problems where I've asked you to calculate the log of a complex number. This is the formula for it, okay? So you can do it, yeah. Yes, sir?
We would also specifically take the punctured plane because the argument of 0 doesn't quite make sense, right?
Yeah, well, that's part of it, but the other I mean, that's true. Very good point. But worse yet, like natural log of absolute value of 0, like that, we can't do that. Because that's just plain old real natural log there. All right. Notice I'm making a technical distinction between ln versus log. So sorry, you Mathematica people. The definition: cosine of z and sine of z. All right. So in your homework, I ask you to discover that for the imaginary exponential, you have the following formula, but with theta, not z. It turns out that this is a good transitional definition for cosine, and a good transitional definition for sine. You can, I ask you to use these in the homework. In the case that z is real, excuse me, like if you look at e to the I theta equal to cosine theta plus I sine theta, right? You can solve this for cosine theta is 1/2 e to the I theta plus e to the minus I theta, and sine theta 1/2i e to the I theta minus e to the minus I theta. But the difference conceptually is those are real theta in your homework, all right? That theta is real. Here, I'm saying z is complex. This is the complex sine and the complex cosine, all right? So that's the definition for now. We can also talk about hyperbolic cosine and hyperbolic sine. And it's the same formulas, but what? Without the I, right? So what does that mean about the relation of cosine and cosh and sine and sinh? Are they related? Check this out. So what if we do cosine of iz? What do you get?
Wouldn't you just get cosine of z? Because you basically just...
No, I said cosine of iz.
Oh.
Cosine of iz. So e to the I iz plus e to the minus I. You were talking about cosh of iz, and you're right. So I got you. So I, also known as -1, right? So what you got? You got yourself 1/2 e to the minus z plus e to the, well, z, which is what? Yeah, it's cosh. And how about sine of iz? How's that go? Well, let's be careful. We got 1/2i e to the I iz minus e to the minus I iz. How's that work out? Yeah. Negative, yeah. And what about that I? That I down there is kind of, what do we do with that? Here's a question for you. What's 1/I equal to?
I cubed.
I cubed. That's true. Very good. I cubed. That is a wrong but correct answer. So minus.
If you're going to say pi to negative pi, then you're allowed to say.
I didn't say that. That was decided long before I was born. It's in books. I have proof. So minus I. So this is really, check this out. I times 1/2 e to the z minus e to the minus c. See what I did? I took the minus over here and I distributed it through there and flippity-flopped them, and now I've got my e to the z. And what do I got? Well, I got myself an I sinh z, don't I? You don't have to memorize these, but you certainly should be ready to derive them at a moment's notice, all right? Now here's a question. What are the component functions of these functions? Well, you know, so We'll look at those in like your upcoming homework probably, all right? Like homework 2, not the one that you're doing at the moment, but let me do some of that. The thing is, so just to tell you, the adding angles formulas are still true for complex sine and cosine. You can work it out. And because of that, like let me just do something specific. Let's work on sine. Let's find the component functions for sine. I think we've got time for that. So let's do 2 things with the time that remain. Let's look at example, where am I? 28. Oh yeah, thanks. I've never done 28 examples in a Tuesday, Thursday class before. Thank you. So f of z equals to sine of z. All right, but I'm going to look at that as sine of x plus iy. All right. Now, you'll have to take my word for it for the moment until you prove it in a future homework. So we're taking out a logical loan from one of your future homeworks. But this is sine of x, cosine of iy, plus, well, cosine of x times the sine of iy. So the adding angles formula actually still true. And guess what? We just worked out cosine and sine over here, right? So like cosine of iy is what? Cosh y, right? And then over here, sine of iy is I times sinh, right? So I cosine x sinh y. So you can calculate what's the modulus of sine of z? Square root of what? Now here that square root thing is probably the way to go. Like the only way to go. I got sine squared x, cosh squared y, plus cosine squared x, sinh squared y. How do you simplify this? Any ideas? Remember how cosh and sinh work? We've got cosh squared y minus sinh squared y equals to 1. So I can trade my cosh squared for a 1 plus sinh squared. And then what do I got? I got square root of sine squared x times 1 plus sinh squared y. There might be an easier way through all this. I feel like I'm not going about this optimally. And then what happens? Oh, look at that. Something nice happens, doesn't it? See, because if we multiply this out, we get this sine squared and that cosine squared. They're both multiplied by sinh squared, so they add together to give us 1. And we just get like square root of sinh squared x. Oh man, this is useless. Sine squared x plus sinh squared y. Is that right? I think that's right. I'm just tired enough not to believe myself.
Read it out.
There's, yeah. So this is good. When can this be 0? So this is one way to it. So if you're trying to find out when is a function 0, there's a couple different approaches. One approach is to take the absolute value of the function, see where the absolute value is 0, because it can only be 0 if the absolute value is 0, right? The other way is just to set it equal to 0. So like that would be the other way to find where sine of 0 is. I could study like, you know, sine x, cosh y equals to 0, and cosine x, sinh y equals to 0. So this would be tantamount to sine of z is equal to 0. Look, cosh y, is cosh y ever 0? You guys know what cosh y is? No, yeah, that's a problem. That's going to be a problem. You got to figure that out. So this is cosh y. Let me say cosh of t, all right? It's like a parabola that goes up from 1. Its smallest value is 1. It's never 0. Cosh of y is never 0. So this implies sine of x is 0. Right? What does sinh look like? I better tell you. Sinh is this thing. It looks like a cubic, but it's not. It's exponential both ways. Sinh is in fact injective. It's a one-to-one function. It's everywhere increasing. Its derivative is cosh. But cosh is always positive, which means sinh is always increasing, which means the only place sinh is 0 is 0. The solution of this, then, right?
Y would have to be 0 and x has to be a multiple of 2 pi. Right?
Well, how about this? These have to be solved in concert, right? And you can kind of see it more from up here. The only way to make this so up here it's more clear. How can this be 0? You can't have it 0 if this is non-zero because you're adding 2 squared, it's sum of real numbers squared. That has to be 0 to get this all together to be 0. So that forces us to have sine of x equals to 0 and sinh of y equals to 0, which we're going to get to down here as we keep thinking through it. Let me summarize this. When is the complex sine 0? What are the zeros of complex sine?
0, same as the real.
Exactly, they're just the same as the real sine. They're only where sine of x is 0, which is integer multiples of pi. I heard something about analytic continuation. Them's fighting words. No, I mean that's the welcome comments like two months from now. But yes. Anyway. Oh, I seem to have used my extra 2 minutes. Sorry. I think I started late last time, right? So I owe you 2 minutes. Am I right? Anyway, if you guys have questions about the homework, bring them to me.